Today on Macaulay Math, we review quadratic functions and the quadratic formula. Intro. Okay, good day. I am Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 4 on the quadratic formula. Our goals for today. We're going to analyze the graph of a quadratic function. We're going to write quadratic functions in standard, vertex, and general form, and we're going to use quadratic functions to model data. This lesson covers quadratic polynomial functions. Quadratics are curves that have many applications in physics, including projectile motion, and in finance when relating the quantity of an item sold and the item's selling price. Let's get started.
Okay, so the general form of a quadratic function is going to be y equals ax squared plus bx plus c. The degree of any polynomial function, not just a quadratic function, is always the term with the highest power. And so in this case, the ax squared is the term with the highest power. It is 2. So the degree of a quadratic function is going to be 2. The number of terms, there are 1, 2, 3 terms in this particular quadratic function. The leading coefficient is the coefficient of the leading term, and the leading term will always be the term with a variable of highest degree. So in this case, the ax squared term is the leading term, and its leading coefficient will be a. The constant term, constant meaning it doesn't change, and since x in both of these two instances are variables, the only of these three terms that do not change is going to be c. The linear coefficient, a linear term, regardless of whether it's a quadratic or a higher degree polynomial, will always be the term whose degree is 1. So bx, and again to the first, even though we don't write it there, will be the linear term, and so the linear coefficient will just be b, and the linear term will be bx. Parts of a quadratic function, if we take a look here, the x-intercepts here are both labeled in red. The y-intercept, the place where it crosses the y-axis, is labeled here in green. The axis of symmetry is an imaginary line that divides the parabola in half. And so if I were to fold along this dotted purple line, this portion of the quadratic graph would line up with the other portion of the quadratic graph. The formula that you need to calculate the axis of symmetry can be given by the form x equals negative b over 2a. And where do I get this b and this a? It comes from this general form of the quadratic function. I find out what this number is and I plug it in. I find out what that number it is and I plug it in to this formula right here, and we can calculate that axis of symmetry, and x equaling any constant as a graph will always be a vertical line. If I want to find the vertex here marked in blue, at least in the general form, will be found by taking whatever value you calculate for the axis of symmetry and plugging it into the formula to get the y value. So the axis of symmetry and the vertex have the same x value. Note, the value of a has a significant influence on the shape of the quadratic. If a is greater than 0, then the quadratic opens up. If a is less than 0, then the quadratic opens down. The closer to 0 that the absolute value of a is, and I put this in quotes, wider the quadratic is, and the larger that the absolute value of a is, and again, put in quotes, narrower the quadratic is. So a quick Desmos demonstration to kind of demonstrate the value of a and its effect on the shape. If we look here, we have a very simple quadratic formula. F of x is equal to ax squared. There is no constant term, there is no linear term, and I have a as a slider, so I can change a. Right now it is 1, and if I make a bigger, more positive, you can see that it is making the parabola look a little bit narrower. Now, we've talked about transformations, and in a transformation sense, it's actually stretching it vertically. And then the closer I get to 0, and it gets real quick here, the closer I get to 0, the wider that parabola is going to get. And the moment that I make it negative, now it's opening down. And so the same thing applies. And when they say the absolute value of A gets bigger, then it gets narrower, we see that again it's getting narrower. But again, it's just going to be a vertical stretch with a reflection about the x-axis. The standard form of the quadratic equation is normally called the vertex form of the quadratic equation, and it is of the form y is equal to a times the quantity x minus h squared plus k. In this case, h and k is the vertex, so you can just take it from the formula. And the one thing that students miss is that you'll notice in the form of the equation, h is negative and it's positive here. So whatever number you have here, we're just going to switch the sign to get the vertex. So a couple of quick examples that are in standard form. We have y equals x plus 4 quantity squared. In this case, if I'm looking at it, just to kind of go over some of the values here, a would be equal to 1. My h would be equal to negative 4. And so you'll notice here I'm changing the sign just because h here is negative and h here is positive. So whatever I have, I change the sign. And if I wanted to find the vertex, I would say that the vertex is at negative 4, 0, because there is no value for k. No value for k implies 0. All right, this one here is both in standard form and it is in general form. It's just not written in descending order. In this particular instance, the value for a is negative 1. The value for h in this particular instance is going to be 0 because there is no parentheses with a operation inside those parentheses. K in this case is going to be 3, and so our vertex will be at 0, 3. Now we can check those both real quick. We go over to decimals. And our first one was f of x is equal to x plus 4 quantity squared. And if we want to find a vertex, all we have to do is click on that vertex, and we can see that it is in fact negative 4, 0. In the second example, we had g of x is equal to 3 minus x squared. And we can see that this one, because the leading coefficient is negative, it opens down. And our vertex is, in fact, at 0, 3. How to find parts of a quadratic for either form. In our standard form of a quadratic, the y-intercept is always going to be at 0, c. To find the axis of symmetry, we're always going to go x is equal to negative b over 2a. And then to find the vertex, we are going to plug the value of the axis into the function to find y. And once we've done that, we will have our vertex. So it'll be whatever this value is, and then after you've plugged it in, that y value. In vertex form, our vertex can be read directly from the function. So it will be h and then k. The axis of symmetry, since the vertex lies on the axis of symmetry, it will have the same x value. So the h value from the vertex is the value of the axis of symmetry. Now, the y-intercept, if you remember, anytime a function crosses the y-axis and any point on the y-axis has an x value of 0. So to find the y-intercept, we will plug 0 in for x to find the y-intercept. Okay, example. Given the function f of x is equal to negative quantity x squared plus 3x minus 4, describe the graph of this function. So part A, just for the sake of being able to see it a little bit easier, let's distribute this negative and say f of x is equal to negative x squared minus 3x plus 4. That's just me distributing the negative to all those terms. That the graph of this function is a parabola that opens down Identify the vertex and all intercepts. Okay, well, if I leave this negative here, what I can do is I can try and factor this thing. And if you go back to your Algebra 2, we know that this thing will have two factors. Since it is x squared, we'll still have that negative out front. So I'll have x and I'll have x. And then I need two factors of negative 4 that add up to 3. Well, positive 4 and negative 1, those things add up to positive 3. And when I multiply 4 and negative 1, I get negative 4. So I feel fairly confident in that. And that will give me my x-intercepts. And so my first x-intercept will be negative 4, 0. Because when I plug in negative 4 here, I'll get 0 out. And the other one will be 1, 0. Because when I plug in 1 here, I will get 0 out. To find my y-intercept, I will look at this second function, and now that I have everything simplified, my y-intercept will be at 0, 4. And then I will verify these things by plugging my original function into Desmos. Okay, here is my function, and we can see by clicking on the intercepts, we have a parabola that opens down. It has an x-intercept at negative 4, 0 and 1, 0, and has a y-intercept at 0, 4. So that matches all of the things that we have for that. Completing the square review, change the general form into standard form. So we're going to use completing the square to do that. And so just as a quick review, we want to make sure that the a value is equal to 1. So the way that we're going to do that is we are going to factor out the 2 from these first two terms. And so 2x squared divided by 2 is just x squared. 8x divided by 2 is just 4x. And then I have the minus 14 here on the outside. I left some space in here to complete the square, which is my next step. And so here I am going to add and subtract b over 2 quantity squared from the same side. And so we'll go y is equal to 2 times the quantity x squared plus 4x. And then I'll have minus 14 here on the outside. So on the inside, what I'm going to do is I'm going to add b over 2 squared. Now b in this case is going to be 4, so I'm going to add 4 over 2 quantity squared. And then because I'm adding it and I want to keep everything balanced, I have to subtract it away on the outside to keep it balanced. But because it's inside these two parentheses, I have this 2 on the outside that has to be distributed to each term. So again, to keep it balanced, I have to keep that 2 on the outside as well. So I have now completed the square. This is y equals 2 times. This is a perfect square trinomial. It is x now plus, well, 4 over 2 is 2, and it is squared. And then again, 4 over 2 is 2, squared is 4. 4 times 2 is 8, and then 14 minus 8 is negative 22. Now, I feel fairly confident in that, but let's go to Desmos and check to make sure that both of these two forms are the same. All right, so we have f of x is equal to 2x squared plus 8x minus 14. That was our original function. And our vertex form will be g of x equals 2 times the quantity x plus 2 quantity squared minus 22. And we see that both of these equations do line up perfectly. And in each case, our vertex is at negative 222. And if we look at our vertex form, remember we would take the opposite value here. So negative 222 is our vertex. The quadratic formula, hopefully you have this memorized from your Algebra 2 class. But we use this to find all of the zeros of a quadratic polynomial. It will find your integer zeros, your rational zeros, your irrational zeros. It will even find your imaginary zeros. So you should have this in your long-term memory. If you have a standard form quadratic equation, then you can take the A, the B, and the C and plug them in these respective spots in the quadratic formula and get those zeros. So if we want to find the zeros for this thing, and I can tell you right up front that I could factor this, so I'm doing an elementary example to show that the quadratic formula does work. And so in this case, the value for A would be 1, the value for B would be negative 1, and the value for C is going to be negative 6. So I am just going to take those values and I'm going to plug them back into this quadratic formula. So I will have x is equal to, well, if b is already negative 1, then negative b would be positive 1, plus or minus, meaning both the positive and the negative, and then I'll put my square root symbol. Remember, if you're typing this into a calculator, even Desmos, that if you're going to square a negative, you need to put it into the parentheses. Minus 4 times a, which is 1, times c, which is negative 6. And this will be all over 2 times a, which in this case is 1. And so we will evaluate what's underneath my radical here first. So I have my 1 plus or minus the square root. Now, negative 1 squared is positive 1. 4 times 1 times negative 6 would be negative 24. So I have 1 minus negative 24, which would be the same as 1 plus 24, which is 25. And that'll be all over 2 times 1. And so we can simplify that. We have 1 plus or minus. The square root of 25 is 5. 2 times 1 is 2. And so 1 plus 5 is 6. Divided by 2 is 3. 1 minus 5 is negative 4. Divided by 2 is negative 2. So these are the zeros of that quadratic polynomial. And they are the values where this quadratic function would cross the x-axis. So we can check our work pretty easily by going to decimal. And so if I make that quadratic equation a quadratic function, then the values for x that make this thing equal to 0 will be the x-intercepts. And we found the first x-intercept to be at negative 2 and the second x-intercept to be at positive 3, which matches our results. All right, last example. Application problem. A child care center has 200 feet of fencing to enclose 2 adjacent rectangular safe play areas. Additionally, the facility uses one side of the center as a wall. Determine the dimensions that will produce a maximum enclosed area. All right. So what they're saying here, let's draw a picture. And so here is my side of my daycare facility. And then what they do is they are going to take and they're going to draw a rectangular playpen that is split into 2. And we have 200 feet of fencing to do this, and so we want to maximize the area inside these two boxes. So here's what I'm going to do. I'm going to call this X, I'm going to call this Y, and we want adjacent rectangular safe play areas, and we want the maximum area inside these two adjacent safe play areas. And so this 200 feet of fencing is this wall, this wall, this wall, and these two walls. So just to make it simple, what I'm going to do is I'm going to make from here to here Y, and then this one will also be Y, and then these three parts right here will be X. So the sum of these three X's and these two Y's has to equal the 200 feet. So I am going to say that 200 is equal to 3x plus 2y. Now this is a secondary it doesn't actually find area. But if I'm telling you that I want to have the maximum amount of area, then in general I could just pick larger and larger values of x and y. So for me to be able to maximize an area, I have a constraint. It is the secondary equation. I only have 200 feet, so that puts limits on what I can make for the area. The area for any rectangle, we remember to be area is equal to length times width. Now we are trying to produce a maximum area, so we're trying to make A as big as we can. In this particular case, A is going to be equal to just X and Y. Now that's not the total area, that's just the area of this one rectangle, but since they're equal, if I maximize this rectangle, I'll maximize both of them. Now I have 1, 2, 3 variables. This is where I come into a little bit of a problem. So what I'm going to do is I am going to take this secondary piece of information and want to go 200 is equal to 3x plus 2y, and I'm going to solve it for y. And to do that, I'll flip this equation over and subtract 3x from both sides. So I'll have 2y is equal to 200 minus 3x, and then I will divide both sides by 2. So I'll have y is equal to 200 divided by 2 is 100. And then negative 3x divided by 2 will be negative 3 halves x. And so what I'm going to do now is I'm going to take this and I'm going to plug it in for y. And what that's going to allow me to do is now I have a single equation in two variables. And let's distribute. So A is equal to 100x minus 3 halves x squared. And I know something about this. This thing is a parabola that opens down. All right, so I know something about it. It has no value for c, so their y-intercept will be 0. So I have a parabola that has to look something like this. Here is x, and I see x being this length right here. And this axis is not y, it's actually a. It's the area axis. So this point right here, this vertex, this is the maximum area. So let's go back and make sure we get the question. It wants us to determine the dimensions that will produce a maximum enclosed area. So we want to find not just the max area, but we want to find this x value right here, and that will be one of the dimensions that find the maximum area. Now we could do the quadratic formula, we could do a bunch of things if we wanted, but let's use decimals to solve this. So we will type that function in and we will go f of x, remembering that f of x in this case is the area. We will go 100x minus 3 divided by 2, so there's my 3 halves. I hit my right arrow key so that I get out from the denominator x squared, And we already know that this thing has to be a parabola that opens down. It has to look something like this. Now, if I look at my graph, all I see is that first part. So I need to open up Desmos so I can see what I need to see. So what we're going to do is we're going to talk about the powers of 10 way to figure out your window. And so what I'm going to do here is I am going to just increase my x values by powers of 10 until I see what I need to see. So I start with a 1, I hit 0, that's 10. I increase it by another power of 10 to get to 100, and clearly now I see both of the two x-intercepts. I knew this has to be. Now, the y values aren't nearly tall enough. So again, I'm going to do the same thing, but I'm going to do it with the y's to get to the top of that parabola. So I'll clear out what was there. I'll start with 1, and I'll just add powers of 10 until I see what I want to see. So the first one gives me 10, the second one gives me 100, the third one gives me 1,000, and I have a fairly good idea that if I go up another 0, it'll be too big. So what I'll do is I'm just going to change this to 2,000, and clearly here we see what I need to see. And so this value right here, what this thing tells me is that when I make the x value 33 1/3, my maximum area is going to be 166.6 repeating feet squared. And so here's what I'll do. I know that the maximum x value, this is 33 1/3, 33.3 repeating, and that is the x. So my dimensions will be 33 1/3 feet by, now I need this y value here, and even though we've done a whole lot on this one, it's real simple. I have a formula that we made for the y value. So what we'll do is we'll plug that 33 1/3 in for x. And so I'll go y equals 100 minus 3 divided by 2 times 33 1/3. Okay, well, 33 1/3 times 3 over 2 will end up being 50, and you can check that if you want. And then 100 minus 50 is 50. And so my dimensions will be 33 1/3 feet by 50 feet. And if I check myself, 33 1/3 plus 33 1/3 plus 33 1/3 is 100. 50 and 50 is 100. 100 and 100 is 200. So I have used all 200 feet of the fencing, and I have maximized my area. And that is where we will end it. To the Star Wars fun fact of the day. Alec Guinness played Obi-Wan Kenobi in Star Wars Episodes 4 through 6. He won the Academy Award for Best Actor in 1957. To get him to play the part, which he thought of as fairy tale trash, they offered him 2% of the gross receipts, which earned him $97 million by the time of his death. More than any other movie that he was ever in. So, good thing for fairy tale trash. Gotta love Star Wars. That's all I got for today, folks. Have a good day. Bye.